In this video, I'm going to go through the calculations questions for tutorial 2.1 on Bohr's atomic model. For B is the first calculations question. So we have been given the wavelength 656.3 nanometer and we are being asked to find the frequency for the photon emitted. So that is step number 1, identify what I've been given. So in step number 2, we need to choose an appropriate formula in order to calculate frequency and having the wavelength in it. So basically, this is the formula that we can use. The mu here represents frequency, and the c here represents speed of light over lambda. So the lambda here refers to the wavelength. So to calculate the frequency, basically speed of light is a constant 3 times 10 to the power of 8 meter per second. Divide with the wavelength. So the wavelength here is given in nanometer, but in order to do the division, the unit must be in meter. So before we can put it in, we need to do the unit conversion. So 656.3 nanometer. So how can we convert it to meter? We know that 1 nanometer is equivalent to 1 times 10 to the power of negative 9 meter. So to cancel the nanometer, the 1 nanometer should be the denominator. And 1 times 10 to the power of negative 9 meter will be the numerator. Then we can cancel the nanometer to give us the wavelength in meter. Then we can substitute into the formula to give us the frequency of the photon emitted as 4.573 times 10 to the power of 14 per second. The next calculations question is question number 5b. So for question number 5b1, we have been given fourth line in the Lyman series and we want to calculate the wavelength of the photon that is being emitted. So from what is being given, Lyman series, we know that the lower energy level must be n equals to 1. And then to find the higher energy level, we know that we need to use lower energy level plus the number of the line. So the lower energy level is n equals to 1 and it is fourth line, therefore plus 4 to give us n equals to 5 as the higher energy level. Then second step, we need to choose appropriate formula. So we have the electron transition and we want to find wavelength. So therefore, Ribot equation for wavelength is the formula that we should use. So Ribot equation for wavelength, n1 should be smaller than n2. So as n1 should be smaller than n2, therefore n equals to 1 will be n1 and n equals to 5 will be the n2. With that, then we can substitute into the Ribot equations for wavelength. So the Ribot constant that we need to use is 1.097 times 10 to the power of 7 per meter. N1 is 1, N2 is 5, and we should get our wavelength in meter because the Ribot constant is having unit per meter. So that is equal to 9.496 times 10 to the power of negative 8 meter. But the questions want it to be in nanometer, and we know that 1 nanometer is equivalent to 1 times 10 to the power of negative 9 meter. Now we want to cancel the meter so that we can get the answer in nanometer. Therefore, the 1 times 10 to the power of negative 9 meter should be the denominator. So that we can cancel out the meter. And then 1 nanometer should be the numerator to give us the wavelength in nanometer as 94.96 nanometer. To calculate the frequency, another formula we need to use. So that is this formula. So we want to calculate frequency nu. We use speed of light divided by the wavelength. So speed of light is a constant having the value of 3 times 10 to the power of 8 unit meter per second. And since the speed of light is having the unit meter per second, therefore the wavelength of photon that we need to use must having the unit of meter. So 9.496 times 10 to the power of negative 8 meter. Cancel the meter to give us the frequency of the photon as 3.159 times 10 to the power of 15 per second. So this is answer for 5b1. So for 5b2, we do the same thing. But now, this is Balmer series. Balmer series, and it is fifth line in the Balmer series. So Balmer series, the lower end should be n equals to 2. To find the higher end, it is lower end plus the line. So there is fifth line, therefore the higher energy level is n equals to 7. With that, then we substitute into the Rybert equation for wavelength. So we write down the formula first, and n1 should be smaller than n2, so therefore n1 is n equals to 2 and n2 is n equals to 7. Then substitute into the equation, Rybert constant 1.097 times 10 to the power of 7, n1 is 2, n2 is 7, to give us the wavelength as 3.970 times 10 to the power of negative 7 meter. To convert it to nanometer, again, need to use 1 times 10 to the power of negative 9 meter as a denominator and 1 nanometer as the numerator, so that we can cancel out the meter to give us the wavelength of photon in nanometer as 397 nanometer. To calculate the frequency, again we use the formula frequency is equal to speed of light divided by the wavelength. So speed of light 3 times 10 to the power of 8 meter per second. Wavelength, we need to use the wavelength in meter. Cancel out the meter to give us the frequency of the photon as 7.556 times 10 to the power of 14 per second. So for question number 6a, we have been given the wavelength for red line, and we want to calculate the energy of photon emitted. So in step number 2, we want to choose appropriate formula that relate wavelength and the energy of photon emitted. So that would be combination of these two formula. So energy of photon equals to Planck constant multiplied by speed of light divided by the wavelength of the photon emitted. So H here is the Planck constant, 6.63 times 10 to the power of negative 34 joule second. And then C here is speed of light, 3 times 10 to the power of 8 meter per second. And the wavelength here, it must be in meter, because the speed of light given the unit is meter per second. In order to divide, the unit must be consistent. So how do we convert the wavelength to meter? So again, we know that 1 nanometer equivalent to 1 times 10 to the power of negative 9 meter. To cancel the nanometer, so 1 nanometer should be the denominator. And 1 times 10 to the power of negative 9 meter should be the numerator, to give us the wavelength in meter as 656.3 times 10 to the power of negative 9 meter. So then substitute into the formula to give us the energy of photon for the red line as 3.031 times 10 to the power of negative 19 joule. So the question is not asking us to convert to kilojoule, so it's not a need to convert it to kilojoule. You can leave your answer in joule. So how about the green line? So for the green line, it's the same thing. We use the energy of photon equal to Planck constant multiplied by speed of light divided by the wavelength. So the Planck constant, 6.63 times 10 to the power of negative 34 joule second. Speed of light, 3 times 10 to the power of 8 meter per second. Divide by the wavelength. So again, convert it to meter by multiply with 1 times 10 to the power of negative 9 meter. 1 nanometer as the denominator, because we want to cancel out nanometer, to give us the wavelength as 486.3 times 10 to the power of negative 9 meter. Then substitute into the equation to give us the energy of photon that produce green line as 4.090 times 10 to the power of negative 19 joule. Again, the question is not asking in kilojoule, so you can just leave your answer in joules. So question number 6b1, we want to determine the electron transition for red, blue, and the green line. So we are going to look at the red line first. And what is electron transition? Basically, electron transition is referring to movement of the electron from which higher energy level to which lower energy level. From higher energy level to lower energy level, because in the syllabus you are learning about emissions line spectrum, so it must be from the higher energy level to lower energy level. So we have been given red, green, and blue line. So these are in the visible light region. So therefore, for this line spectrum, it is the Bohr series. So by knowing which series, then we know that the lower energy level must be n equals to 2. And now we need to find what is the higher energy level. And we know that for red line, this is the wavelength, 656.3 nanometer. So which formula should we use in order to find the higher energy level? So basically it's this formula, 1 over lambda equals to Rybert constant multiplied by 1 over n1 squared minus 1 over n2 squared with n1 smaller than n2. So basically n1 is smaller than n2 according to the formula. Therefore our n1 here must be n equals to 2 and we are looking for n2. And the wavelength must be in meter because the Rybert constant is in per meter. So the wavelength in meter should be 656.3 times 10 to the power of negative 9 meter. With that, then we just need to substitute into the equation. Rybert constant 1.097 times 10 to the power of 7 per meter. And then n1 is n equals to 2. So 2 squared minus n2 squared. So n2 is the one that we want to find. So you just need to key this into your calculator and you should be able to find your n2 as 3. So therefore, the electron transition is from n equals to 3 to n equals to 2. And for the green line, we do the same thing. Use the Rybert equation for wavelength. So n1 again, because this is also Bohr series, so it's n equals to 2, and we want to find n2. So for green line, is 486.3 times 10 to the power of negative 9 meter, the wavelength. So substitute that into the Rybert equation for wavelength. So Rybert constant 1.097 times 10 to the power of 7 per meter. 1 over 2 squared, and we want to find n2. So n2 for green line is equal to 4. Therefore, to produce green line, the electron transition is from n equals to 4 to n equals to 2. To calculate the electron transitions in producing blue line, it's also the same. We use the Rybert equation for wavelength. And we know that this is Bohr series, so the n lower is equal to 2. And we want to find higher energy level. And therefore, n1 should be n equals to 2, and we want to find n2. And for the blue line, the wavelength is 434.2 times 10 to the power of negative 9 meter. With that, then we just need to substitute into the equation. We must convert the wavelength to meter because the Rybert constant is per meter, so the unit must be consistent. And n1 is 2, so 2 squared minus 1 over n2 squared. And you just need to key in the calculator and you should get your n2 equals to 5. Therefore, the electron transition in producing the blue line is from n equals to 5 to n equals to 2. And 6b2, you need to sketch the energy level diagram for red, blue, and green lines. So how to do that? So first, sketch the energy level diagram. So the energy level n equals to 1. So, and then n equals to 2, n equals to 3, n equals to 4, so n equals to 5, n equals to 6, and then n equals to 7, and then dot 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 dot. So infinity, where many energy level overlap with one another. And don't forget, the axis is energy, the y-axis is energy. To produce the red line, so electron move from n equals to 3 to n equals to 2. So that electron transition will produce the red line. And then to produce the green line, so electron move from n equals to 4 to n equals to 2 in order to produce the green line in the Bohr series. To produce the blue line, electron fall from n equals to 5 to n equals to 2, producing the blue line in the Bohr series. So this is how you use the energy level diagram to show the electron transition in B1. For question number 7, we are being given the difference in energy, and we know that the difference in energy is equal to the energy of photon emitted numerically. And then we want to calculate the wavelength of the photon. So this is the step 1, interpret first the question, and step number 2, we need to find a formula that relates wavelength and the energy of photon. So there is combination of these two formulas. So energy of photon is equal to Planck constant multiplied by the speed of light divided by the wavelength. Energy of photon given is 4.09 times 10 to the power of negative 19 joule. Planck constant is 6.63 times 10 to the power of negative 34 joule second. And the speed of light is 3 times 10 to the power of 8 meter per second. And we want to find the wavelength of the photon emitted. So just need to key in your calculator and you should be able to get the wavelength of the photon emitted as 4.863 times 10 to the power of negative 7 meter. So the questions never ask us to convert to nanometer, so we can just leave the answer in meter. So the second part of the question, want to calculate the frequency of the photon. Again, we have the energy of the photon, and we want to calculate the frequency of the photon. Therefore, the formula that relate the energy of photon with the frequency of photon is this formula. So energy of photon equal to Planck constant multiplied by frequency of the photon. And the energy of photon is 4.09 times 10 to the power of negative 19 joule. Planck constant is 6.63 times 10 to the power of negative 34 joule second. And we want to calculate the frequency of the photon. And the frequency of the photon, therefore, is equal to 6.169 times 10 to the power of 14 per second. For question number 8a, the questions ask us to draw the energy level diagram to show the transition for the line A, B, C, and D. So again, for the electron transition means that we want to find the higher energy level is n equals to what? To lower energy level, which is n equals to what? And for this question, we have been given visible light region. So visible light region means that this is Bohr series. So if Bohr series means that the lower energy level must be n equals to 2. And for the first line, which is A, we want to find what is the higher energy level. So higher energy level basically is equal to the lower energy level plus the number of the line. So lower energy level is 2 and the number of line is 1. A is first line, so 1. So therefore, the higher energy level is equal to 3. So to produce line A, basically electron transition is from n equals to 3 to n equals to 2. For line B, to find higher energy level, so again it's lower energy level plus the number of the line. So lower energy level, this is Bohr series, so it's equal to 2, and B is second line. So therefore plus 2 to give us higher energy level as 4. So therefore to produce line B, it must be corresponding to the electron transition from n equals to 4 to n equals to 2. For line C, again, to find the higher energy level, formula lower energy level plus the number of the line. Balmer series, lower energy level, n equals to 2. So C is the third line. Therefore, plus 3 gives us 5. Therefore, to produce line C, it is corresponding to the electron transition from n equals to 5 to n equals to 2. For line D, again, higher energy level is equal to lower energy level plus the number of the line. Again, this is Balmer series, so lower energy level is n equals to 2, and D is the fourth line. Therefore, plus 4 to give us higher energy level, n equals to 6. So to produce line D, basically is corresponding to electron transition from n equals to 6 to n equals to 2. The question asks us to draw the energy level diagram to show the electron transition. Therefore, to draw the energy level diagram, first we need to draw the axis energy, and then energy level n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, n equals to 6, n equals to 7, and then dot dot dot. At infinity, many energy levels overlap with one another. To produce line A, it is corresponding to electron transition from N3 to N2. So the electron transition will give line A. For line B, it is corresponding to electron transition from N4 to N2. So N4 to N2. So we'll give line B. And then to give line C corresponding to electron transition from N5 to N2. N5 to N2. So produce line C. To produce line D, it is corresponding to electron transition from N6 to N2. So N6 to N2 to give line D. So this is how we draw the energy level diagram to show the electron transitions for line A, B, C, and D. And the emission series that produce the lines is Balmer series because occurs in the visible light region. For question number 9a, we are being given the frequency of a photon and asked us to calculate the wavelength of the photon. So which formula that relates frequency of a photon with the wavelength of the photon? So this is the formula. So therefore, we need to use this formula, frequency of photon equals to speed of light divided by lambda to calculate the wavelength of the photon. Frequency of photon 6.6 times 10 to the power of 15 per second. Speed of light 3 times 10 to the power of 8 meter per second. And the wavelength of the photon is the one that we are looking for. So by substituting everything into the equation, we get the wavelength of the photon as 4.545 times 10 to the power of negative 8 meter. Since the question not asking in nanometer, we can just leave the answer in meter. For question number 9b, the question asks us to calculate the energy of photon emitted by 1 mole of electrons. And given frequency of the photon corresponding to 1 electron is this. So therefore, to find the energy for 1 mole of electrons, we must first find the energy of the photon corresponding to 1 electron first. So to calculate the energy of photon corresponding to 1 electron, we can use this formula since we are being given the frequency of the photon. So we use the formula Planck constant multiplied by the frequency of the photon. Planck constant 6.63 times 10 to the power of negative 34 joule second. Frequency of the photon 6.6 times 10 to the power of 15 per second, giving us the energy of photon for 1 electron as 4.376 times 10 to the power of negative 18 joule. So this is the energy of photon corresponding to 1 electron transition. The question asks for 1 mole of electron. So 1 mole of electron is equal to 6.02 times 10 to the power of 23 electron. So we want to find what is the energy emitted corresponding to 1 mole of electrons. We know that for 1 electron, it is equivalent to 4.376 times 10 to the power of negative 18 joule. For 1 mole of electron, 6.02 times 10 to the power of 23 electron. So how many amount of energy involved? So it's X. So how do we find X? So basically we can do cross multiplying. So 6.02 times 10 to the power of 23 electron multiplied by 4.376 times 10 to the power of negative 18 joule. We want to find X. So therefore need to divide by 1 electron. Electron we can cancel out to give us the energy of photon emitted corresponding to 1 mole of electron as 2.634 times 10 to the power of 6 joule. So for 1 mole of electron, usually we give the energy in terms of kilojoule. So how to convert this energy to kilojoule? So by divide by 1000. So when we divide by 1000, so we should get 2.634 times 10 to the power of 3 kilojoule. And therefore, the energy emitted by 1 mole of electron is equal to 2.634 times 10 to the power of 3 kilojoule per mole. So here, 1 mole of electron is written in front here. So therefore, the unit just kilojoule. For energy emitted, to tell people this is 1 mole, we need to write the unit as kilojoule per mole to tell people that this is the amount of energy emitted corresponding to 1 mole of electrons involving in the electron transition. Now we look at the last calculations questions in 2.1, ionization's energy of hydrogen atom. We know that to ionize hydrogen atom, we need to move the electron from n equals to 1 to n equals to infinity. By moving electron from n equals to 1 to n equals to infinity, so basically we remove the electron from the atom and make it into an ion. So what is the amount of energy involved in ionize the atom? So basically, to calculate that, we need to use this formula. But remember, for this formula, it is for 1 electron. For 1 electron, we are calculating the amount of energy needed to remove an electron completely from an atom. And then, initial So when using this formula, we need to know where is our initial energy level. So initially, electron is at n equals to 1. Therefore, initial energy level is n equals to 1. And final energy level, at the end, the electron is at infinity. Therefore, the final energy level is n equals to infinity. And for the Rybel constant, because this is energy, therefore, we need to use 2.18 times 10 to the power of negative 18 joule. And then, n initial is 1 squared, and then n final is infinity squared to give us 2.18 times 10 to the power of negative 18 joule. So this is the energy needed to remove 1 electron completely from 1 hydrogen atom. But in ionization's energy, it is defined for 1 mole. 1 mole. We want to remove 1 mole of electrons completely from 1 mole of hydrogen atom. Therefore, we need to calculate the energy for 6.02 times 10 to the power of 23 electron. We know that for 1 electron, it is corresponding to 2.18 times 10 to the power of negative 18 joule. For 1 mole of electron, 6.02 times 10 to the power of 23 electron, we want to calculate what is the amount of energy needed. So to calculate X, so basically we can apply cross multiplying 6.02 times 10 to the power of 23 electron multiplied by 2.18 times 10 to the power of negative 18 joule. We just want to find X, so therefore divide by 1 electron to give us X as 1.312 times 10 to the power of 6 joule. Again, for 1 mole, usually we need to calculate the energy in kilojoule. So to convert it to kilojoule, we need to divide by 1000 to give us 1.31612 times 10 to the power of 3 kilojoule. And therefore, ionization's energy of hydrogen atom is equal to 1.312 times 10 to the power of 3 kilojoule per mole. So per mole here means that it is for 1 mole of electrons. So here is kilojoule because we already write the 1 mole of electrons in front. Okay, so but for ionization's energy, the unit must be in kilojoule per mole because we are calculating for 1 mole of electrons.